Welcome all. So, today we will continue our lecture on multi-degree of freedom system analysis subjected to impact scenarios. Last time we looked into the derivation of the stiffness matrix, we looked into the derivation of the flexibility matrix. So, we will continue with the lecture. So, depending upon the circumstances, we have to see whether we can derive the stiffness matrix directly or the flexibility matrix directly. So, the derivation of the stiffness matrix, the formulation becomes more complex in this scenario because shifting a mode creates shears in both the panels directly linked to that mode and in those that are further away. So, it indicates that the system are far coupled, exhibiting a strong degree of coupling. What it means is that we have a great significance of the cross terms. If you look into the cross terms, they are comparable with the main diagonal term. So, it signifies that the system is heavily coupled. If we multiply the stiffness matrix with the flexibility matrix, we are going to get the identity matrix, thus proving that the stiffness and flexibility are inverse of one another. So, moving ahead. So, now we look into the concept of the strain energy of a system. So, for a system in configuration defined by the degrees of freedom x1, x2, x3 up till xm, the strain energy V denoted by V is equal to the work done by the forces during the given displacement. So, we can write the formulation of the strain energy as a summation of the work done. So, in matrix notation, if we have to write, we write down the matrix notation of the F term, the force term and the displacement term. Or if we can take the transpose and write in both the forms. So, if we substitute the equation for the displacement. So, x we know x is given by flexibility matrix times the force matrix. So, if we substitute it back into the equation, into the equation we get this form. So, here we are substituting x and replacing this by f. Similarly, what we can do is that we can replace f by x. So, if we are replacing here, we will introduce the flexibility term, or if we are doing here, we will introduce the stiffness term. So, both of this are representing the same quantity. In one of the cases, this is all made up of force terms, and in the other cases, this is made up of the displacement terms. So, equation 11, this particular equation is representing the quantity V, the strain energy using the flexibility matrix, that is D, while equation 12, this equation is representing the same quantity using the stiffness matrix. So, both ways we can write down the strain energy. Moving ahead. So, after that what we do is that we, since both of them are representing the strain quantity, we equate them. So, if we equate them, we get this term. So, we prove the identity that the D equals to D transpose, or the flexibility matrix is similar. So, this is nothing but a reinstatement of the Maxwell reciprocal relationship. So, by following a similar approach and substituting equation 4 into equation 10, we again prove that my stiffness matrix is also symmetric. So, here we have proved that the flexibility matrix is symmetric, here we are proving that the stiffness matrix is symmetric. That intuitively also we are getting from the Maxwell reciprocal theorem also. So, this is just an elegant representation of the Maxwell reciprocal theorem in terms of a stiffness matrix. So, my K and D is symmetric, the stiffness matrix and the flexibility matrix is symmetric. So, this result was obtained earlier by using the application of Bette's work principle. So, Maxwell and Bette's both can be used to prove that the stiffness and the flexible matrix are symmetric. Flexibility matrix we are directly getting from the Maxwell, and stiffness matrix we are getting from the Bette's theorem. So, equation 12 represents an expression in the quadratic form. If you look into equation 12 closely, if you look into this equation 12 out here, so it is this equation is representing the strain energy in quadratic form of x, okay, with cross terms also. Okay. So, this is the matrix notation. Same way we can write down this thing in the algebraic form. Okay. So, what it will do is that it will have the x terms, okay, and then it will have the cross terms, okay, and C1, C11, C12, all these things are the coefficients that are coming from the stiffness matrix. So, this is an expression consisting of the sum of the squared displacements. Okay. So, the displacement terms are squared. Okay. So, here we can say these terms are squared and product of the displacement pairs. Okay. So, these are the square terms and these are the products. Okay. So, this equation is a quadratic equation. Okay. So, it will result in a scalar value. Okay. So, this is an algebraic representation of the strain energy in the quadratic form. Quadratic means that x terms are squared. Okay. So, it is positive if its value is greater than 0 for all combinations of variable. It is positive definite if its value is greater than 0 for all combinations except the trivial case, okay, when inherently all the variables value is 0. Okay. So, if this term is greater than 0, okay, so then it becomes a positive definite matrix. Okay. Matrix is positive definite if its associated quadratic form is positive definite. Okay. So, it means that if this algebraic expression is greater than 0, then the corresponding matrix that results in this form is positive definite. Okay. So, a matrix is positive definite if its associated quadratic form is positive definite. Okay. So, if this quadratic form is greater than 0, it means that my matrix is positive definite. Okay. Strain energy is always positive definite. Okay. Its quadratic form and the stiffness matrix are positive. Okay. Since it is in the quadratic form and the stiffness matrix is positive, then stress energy is always positive. Okay. For a fixed base system, strain energy equals to 0. Okay. It only happens when all displacements are 0. Okay. The stiffness matrix remains the positive definite. Okay. So, if no displacement is there, the total strain energy will be 0. Okay. Though the stiffness matrix is positive definite. Okay. Systems with rigid body motion can have 0 strain energy for non-zero displacements. Okay. V and K are positive, but not positive definite. Okay. So, in the rigid body system, we can have 0 strain energy for non-zero displacements. Okay. It means that the strain energy and K are positive, okay, but they are not positive definite. Okay. Positive means that the value is greater than or equals to 0. Positive definite means that the value is greater than 0. Okay. So, then this equality may creep up in case of the rigid body motion. Okay. The mass matrix, if you look into the mass matrix is positive definite because the associated quadratic form. Okay. This is the associated quadratic form for the mass matrix. Okay. And this represents the kinetic energy of the system. Okay. A quantity which is non-zero and non-positive combination of the velocity, except in the trivial case of velocity when the velocity itself is 0. Okay. Simply what it is saying that this quantity, okay, this quantity is the kinetic energy of the system. Okay. So, mass is associated with the kinetic energy of the system, and if we enlarge the quadratic form, okay, if we enlarge the quadratic form of this kinetic energy, then this becomes non-zero. Okay. So, the kinetic energy of the system is non-zero and it is also positive for the combination of the velocities. Since this is a square term, so this will be always positive except in the trivial case when velocity itself is 0, that is the system is at rest. Okay. So, the mass matrix becomes positive definite, okay, because the kinetic energy itself is positive. Okay. So, now we look into the formulation of the dynamic equation of motion of a system. Okay. So, what we have done is that we have taken a discretized system. Normally what happens is that if we take a beam, okay, so in order to describe the motion in space and time accurately, we need the information for all the displacements, okay, all the displacements and the associated rotations at each instant of time. So, it means that the degrees of freedom here becomes infinite. Okay. So, we have to know the continuous information about the vertical displacements as well as rotation. Okay. So, there are infinite degrees of freedom out here. Okay. So, what we have done is that for this continuous system, okay, we have taken a discretized system. Okay. We have discretized the masses. Okay. So, this becomes a discrete system. Okay. And for each discrete part we will have an associated degree of freedom. Okay. So, this is what it is being represented out here. Okay. So, x1, x2, x3, xi till xn are the degrees of freedom. Okay. So, we have taken here as the vertical displacement as the degrees of freedom, okay, and they are taken in the discretized state. Okay. So, what are the resisting forces and what are the external forces? So, external forces is given by the vector of the externally applied load. Okay. So, in this system if any external load is there F1, okay, so this is given, or P1, let us say P1, we are representing here as P1. So, this external force is being represented out here. Okay. So, this force will cause the disturbance in the system or the vibrations in the system. Then on the other side there will be the resisting forces. So, one resisting force will be the inertial forces. Okay. Due to the mass of the system there will be a resistance in the system. So, this will be given by mass times the acceleration of the system. Okay. Then there will be damping in the system. Okay. So, damping we are representing using the velocity. Okay. So, damping normally we represent by C x dot. Okay. That is, we are representing all the damping phenomena as a viscous damping. Okay. So, this x dot represents the viscous damping of the system. Okay. The x dot is the relative velocity and C is the damping coefficient. Okay. So, this term represents the viscous damping. Okay. So, in reality the damping can be of different nature, but we are representing all the effects of the damping using a viscous damping system. Okay. Then there will be the elastic force vector. Basically the stiffness is going to resist the system. Okay. So, that is given by Kx. Okay. So, forcing function side is the externally applied load, resisting side is the inertia force, that is the mass times the acceleration component. Viscous damping, the damping is represented by the viscous damping, so Cx dot, and then the resistance due to the deflection, that is caused by the stiffness times the displacement. Okay. So, these are the resisting forces and these are the externally applied force. Okay. So, here if you look into the matrix form, the mass matrix will be a n cross n matrix. Okay. If you are choosing x n degrees of freedom, if there are n degrees of freedom, then my mass matrix will be n cross n. So, here degrees of freedom are, there are n degrees of freedom. Okay. So, there will be a term till x n. So, mass matrix is n cross n matrix. Okay. And then there will be the acceleration associated which with each of the degrees of freedom. So, basically here it will be x1 double dot, x2 double dot, x3 double dot, and so on and so forth till xn double dot. Okay. So, there will be an acceleration component associated with all the degrees of freedom. After that there will be a damping matrix. Okay. Damping matrix again is going to be n cross n matrix, and with this the velocity terms will be there associated with each degrees of freedom. Okay. So, similarly it will be x1 dot, x2 dot, x3 dot up till xn dot. Okay. The velocity component. Okay. So, here it was mass times acceleration component, here it was stiffness coefficient times velocity component, and after that there will be stiffness coefficient times the displacement component. So, stiffness matrix again will be an n cross n matrix, and the displacement again we know we have chosen n degrees of freedom. So, there will be x n degrees of freedom. Okay. And after that the force vector will be there, and this will represent the external applied forces at each degrees of freedom. If some forces are acting at a particular degree of freedom, then it will be registered here as, let us say, P1. If at any other degrees of freedom the forcing function is 0, then it will be registered here. Okay. So, it will be a matrix of the quantity that is acting on that particular degree of freedom. Okay. So, this is a second order non-homogeneous linear ordinary differential equation. Okay. So, this is the entire representation of a multiple degree of freedom system in the matrix formulation. Okay. So, again as we have already said earlier, so x is the displacement vector, x dot is the velocity vector, and x double dot is the acceleration vector. M, C and K are the symmetric square matrices. Okay. So, that we have already seen that this matrices are symmetric. Okay. So, mass matrix. Okay. Let us talk about the mass matrix. So, what is mass matrix? Mass matrix is a lumped mass matrix. Okay. So, here what we did was we took a continuous system. Okay. Okay. Here we started with a continuous system. Okay. We started with a beam. Okay. A continuous beam. Okay. Okay. So, this was our physical representation of the beam. Okay. Then what we did was we lumped it. Okay. We assumed that in reality there will be infinite degrees of freedom associated with each distance. Okay. So, there are infinite vertical displacements. Okay. So, what we are saying is that we will discretize it. Okay. We will take the degrees of freedom as certain discrete points. Okay. And depending upon that we will lump the masses. Okay, at those degrees of freedom. Okay. So, let us say that this beam has a length of say 10 units. Okay. So, what we can say is that we will choose 10 degrees of freedom. Okay. So, if we are choosing 10 degrees of freedom, then we will lump the masses at 10 places. Okay. So, we will lump the entire mass into the equivalent mass at 10 places. Okay. So, this will become my mass matrix. Okay. So, this is a lumped mass matrix. Okay. It means that only the diagonal terms will be present. Okay. The non-diagonal terms will be 0. So, whatever we are lumping at different degrees of freedom, that will be present out here. So, let us say at first degrees of freedom we have lumped M1, second degree of freedom we have lumped M2, third degree M3 and so hence and so forth. So, there will be Mn masses. Okay. So, only the diagonal terms will be present, the cross diagonal terms will be 0 out here. Okay. So, in this approach we are using a concentrated point mass at each of its corners. So, at each of the chosen degree of freedom we are putting a concentrated point mass. Okay. Then this mass matrix is also a consistent mass matrix. Okay. So, we derived it from the assembly of the element mass matrices, okay, which is based on the shape function used in the stiffness formulation, okay, or any other computational work. Okay. What we are trying to say is that if we remember the first degree of system, okay, or single degree of freedom system, how we derived the matrix. Okay. We derived the matrix using the shape function. Okay. So, in the shape functions we wrote the mass as distributed mass times the shape function squares dx integrated over the entire length. Okay. So, each mass component, okay, we derived using the shape functions. Okay. So, this mass matrix is based on the shape function used in the stiffness formulation. Okay. So, this shape functions we can use in the derivation of stiffness functions, we can use in the derivation of the forcing functions and so on and so forth. So, the same shape functions we are using for the derivation of the mass matrix. So, in the shape functions phi, the numerator represents the mode shape and the denominator represents the value of the mode shape evaluated at the chosen degree of freedom. Okay. So, this is how we make our shape function. Okay. So, for the derivation of mass matrix we have used the shape function. Okay. So, moving ahead. So, the properties of the natural modes and frequencies. Okay. So, what are the properties? So, the first basic property is the orthogonality of the modes. Okay. So, what does it mean? What does the orthogonality means? The modes corresponding to any two distinct characteristic values, okay, natural frequencies are orthogonal both with respect to their inertia matrix and the stiffness matrix. Okay. So, let us now look what does it mean. Okay. So, let omega r and omega be two distinct natural frequencies. Okay. So, there will be n number of natural frequencies, okay, omega 1, omega 2, omega r, omega s till omega n. Okay. So, we are choosing any two natural frequencies, let them be omega r and omega s. Okay. And phi r and phi s will be the associated mode shape. Okay. So, for each frequency, okay, there will be a mode shape. Okay. So, let us choose the associated mode shape. So, for omega r we choose phi r, and for omega s we choose the corresponding mode shape phi s. Okay. So, the first orthogonality condition is, so if we multiply the mass matrix, okay, with the mode shape of two distinct natural frequencies, then that value is going to be 0. Okay. And if we multiply the mode shape with the stiffness matrix, okay, and if the mode shapes correspond to two distinct natural frequencies, okay, then this product is also going to be 0. Okay. So, what we did was we took any two frequencies, okay, omega r and omega s, okay, they are different frequencies, okay, they are not the same, okay, and corresponds to omega r there will be a shape function phi r, and corresponds to omega s there will be a shape function phi s. Okay. So, if we take the shape functions, okay, and if we pre and post multiply with the mass matrix, okay, and since these two are the distinct mode shapes, okay, they corresponds to two different natural frequencies, okay, then this product is going to be 0. Okay. So, this is the orthogonality condition. Okay. If we multiply by any other term, okay, which is not equal to the first term, then the product is going to be 0. So, this is true for the mass matrix also, and this is true for the stiffness matrix also. Okay. So, this is the orthogonality condition. Okay. So, this is the first orthogonality condition, that if we multiply mass by pre and post multiplication with the mode shapes, okay, for two distinct natural frequencies, then the product is going to be 0. And second is, if we do the same treatment for the stiffness matrix pre and post multiplication with the mode shapes corresponding to two distinct natural frequencies, then again the product is going to be 0. Okay. So, these are the two conditions for the orthogonality. Okay. So, if M is diagonal, okay, normally it is, as we have seen in the previous case. Okay. In the previous case we saw that M is normally a diagonal matrix, okay, its cross terms are normally 0, okay, and it comes from the mode shape. Okay. So, normally we are using a concentrated point mass formulation, in which there will be only diagonal terms, non-diagonal terms will be 0. Okay. So, if M is diagonal, as it usually is, as we have seen in this case, so the equation can be equation 15. Okay. So, the orthogonality equation. Okay. So, equation 15 is this orthogonality equation. Okay. This can be written in this particular form. Okay. So, in which Mi is the concentrated mass matrix. What does it doing is that, since we have only the non-diagonal terms, okay, so then what we are doing is that we are writing the non-diagonal terms, okay, rest mass terms are 0. Okay. So, this same equation, okay, since the only diagonal terms are present, non-diagonal terms are 0. Okay. So, we are writing the diagonal terms, okay, in which M1 is the concentrated mass at the ith coordinate. Okay. It means that this is M1, M2, M3, this is Mi till Mn. Okay. So, we are taking Mi, where Mi is the concentrated mass at the ith coordinate, phi ir and phi is are respectively the amplitude of the ith coordinate, where system vibrates in rth and sth natural mode. It means that if we write down the mode shape for rth mode, and if we write down the mode shape for sth mode, okay, then we will have a term corresponding to I. Okay. So, the system is vibrating in the rth mode. So, there will be a mode shape corresponds to I. So, this becomes phi ir, and similarly here there will be a mode value corresponding to ith. Okay. So, in this particular mode shape there will be a mode shape for the ith value. So, this becomes phi is. Okay. So, phi IR and phi IS are these two quantities. Okay. So, if we multiply them, okay, then and if we sum it over the entire mode shapes, okay, then this term is going to be 0. Okay. And the proof is that the modes phi R and phi R must satisfy this particular equation. Okay. And if it is satisfying this particular equation, then the cross terms are 0. Okay. So, this way we can prove the orthogonality of the system. Okay. So, this way, okay, we can take the system and try to prove the orthogonality in the system. Okay. So, we start with k phi r equals to omega r square m phi r. Okay. So, the term corresponds to omega r. Okay. And if we take the s term, okay, this is the equation for the s term. Okay. So, this is corresponding to the rth mode and this is corresponding to the sth mode. Okay. So, we can use this thing to prove the orthogonality of the mode shapes. Okay. So, today we started with the multiple degrees of freedom. We looked into the formulation for the orthogonality, we looked into the symmetric nature, and we tried to prove the orthogonality of the system. So, practice these terms, we will continue for the next time. Thank you.